and welcome to the National Pollution Prevention Roundtable's Safer Chemistry Challenge Program webinar series. Today's webinar is entitled Green Chemistry Case Studies, and we have two excellent case studies from facilities in Ohio. The National Pollution Prevention Roundtable and the Air and Waste Management Association were planning to do a conference in January. However, due to lack of attendance, that conference was canceled, but we've been able to get two of the presenters who are going to be at that conference to participate in this webinar. Just a couple of quick reminders. As you heard, all registrants are in listen-only mode. If you have a question, use the question function on your panel to ask questions. We'll stop after each speaker for questions, and then at the very end, we expect if there are any additional questions, we'll handle those at that time. This webinar is being recorded, and it will be placed on the NPPR website, www.p2.org, by the end of the week. So, with that, I am going to introduce our first speaker, Roy Proctor, who is with Washing Systems. And Roy, go ahead and introduce yourself to the audience and do your presentation.
Thanks, Jeff, and good afternoon, everyone. My name is Roy Proctor. I'm the Vice President of Research and Development for Washing Systems. We're based in Cincinnati, Ohio. Just a little bit about our company. Probably most of you probably don't know anybody in Washington or Washing Systems or have never heard of us. We formulate chemicals for the industrial laundry industry and have grown into one of the largest chemical suppliers to that industry in the U.S. and Canada. We also have a branch in the United Kingdom, and we are basically one of the largest suppliers to the commercial laundry industry in North America. Before I proceed, I'd like to introduce you to the washing process. We pretty much divide the washing process into four areas, that being time, temperature, chemical action, and mechanical action. The law of detergency would state that if one of these pieces is decreased, one or more of the other pieces must be increased to compensate. And I wanted to highlight this because that's going to impact what we do later on with our green chemistry. Here's where we were as an industry, as commercial industry in 2005, as well as Washing Systems itself. The detergents were all pretty much all NPE based, that being nonylphenol ethoxylate based, excellent non-ionic surfactants, but not the greenest surfactants in the world, and I'll go into that later. The builders that we used were phosphate based or EDTA based. We also use an alkali, and obviously we also have specialty products consisting of brighteners, softeners, sanitizers, sours, bleaches, oxidizers, and then also a detergent that basically was primarily a solvent-based detergent. In 2005, the management team at Washing Systems made several commitments, one of which was to deliver products that deliver better cleaning performance, but are also safer for the environment. This aligned better with our core values. Our mission statement says that our mission is to better serve our customers by being the most innovative provider of laundry resource services to the laundry processing industry. If we were successful in achieving these results of better cleaning and better environmental stewardship, our customers would earn more profit, and they in turn would be better stewards to the environment. The Textile Rental Service Association, or TRSA, also expanded Laundry ESP, which was their environmental stewardship program, which was a voluntary Pollution Prevention and Resource Conservation Program with the U.S. EPA. So like I said, we utilized nonylphenol ethoxylates, and it was one of the biggest chemicals of concern for us and for the industry as a whole. They had wide use in detergents, but they also were known to be endocrine disruptors. They had elevated aquatic toxicity, and the byproducts of their degradation were harmful chemicals. There were also existing bans in Canada, Europe, the state of Connecticut, and some other local POTWs. In addition, TRSA entered into a voluntary phase-out of NPEs by the end of 2013 in liquid detergents and the end of 2014 for powder detergents. So to replace NPEs, we had several criteria that we said must be met. We evaluated chemicals that had to have an environmental profile that could pass EPA design for the environment approval or pass green screen criteria benchmark of at least 3. They had to have equal or better performance than their NPE-based predecessor. It had to have the same end-use cost as a detergent than the NPE predecessor had, and there could be no hidden ancillary costs such as increases in wash time, energy use, or water usage. If you look to the right there, you'll see the same wash pie that I showed earlier, but you can see that the time's been increased, the temperature's been decreased, mechanical action's been increased, and chemical action's been increased. A lot of times when our initial work was done to compensate for the lack of NPEs or the green chemistry that didn't work so well, the time or something else had to be increased so that would compensate that. We basically stated you couldn't have increased temperature, time, or other things so that your detergent could work properly. Lastly, we wanted this product to be a one-to-one drop-in replacement for the previous detergent. So basically, you could just switch this detergent for the NPE-based predecessor. It would require no additional changes or incur any additional costs. And the selection method we used to evaluate new chemicals, we primarily used clean ingredients, which lists surfactants, solvents, fragrances, and chelating agents that have preferable environmental profiles. We also used green screen, using fundamentals to identify other potential chemical alternatives not listed on clean ingredients. So in 2007, we achieved our goal of 100% NPE-free detergents. In 2008, we obtained DFE approval of 3 different detergents, that being Eclipse, Essence, and Element, which basically are used in different laundry types, linen, industrial, and also continuous batch washers. In 2008, we also expanded this line with Pinnacle Liquid Detergent. And in 2011, we renewed DFE approval, and we continued to formulate detergents for improved safety and performance. In 2013, we actually expanded our NPE-free detergents by introducing Spectrum and Supreme, both of which obtained DFE approval, as well as Advance in 2014. These are the next generation of NPE-free detergents, as they are concentrated versions, so they also save on freight and packaging, giving additional environmental benefits. What our customers have seen is an economic benefit as they have converted to the green products. Their expectations were exceeded as we have also been able to reduce water, energy, and wash time compared to the previous NPE-based detergent. And just for us, being a small company, the total impact of eliminating NPEs was a reduction of 3.6 million pounds of NPEs per year, for a total thus far of 21.6 million pounds. So that's a big reduction of NPEs going into our waste system. And it also brought our customers regulatory relief for those who were under pressure to switch from the NPEs. We continued to work on greening our entire product line and looked at products other than just NPEs and investigating raw materials that were renewable. We also joined with other green initiatives by joining the National Pollution Prevention Roundtable and entered the Safer Chemistry Challenge 2025. What this Safer Chemistry Challenge did for us, it is aligned with our corporate vision to improve employee health and safety, to minimize risk and liability, to reduce toxins exposed that our employees and also our customers could be exposed to. It would also save materials and energy. It will contribute to the sustainability of our company, and also improve our image as a corporate citizen. What we basically, when we entered into the Safer Chemistry Challenge, when we entered it, we had specific reduction goals in mind for nonylphenol ethoxylates, butyl-salicylate, petroleum-based hydrocarbon solvents, EDTA, and phosphates. When we joined, you can see we achieved a lot of what we had already said we wanted to do. We were well on our way, but still had some work to do. Those other chemicals we looked at, those of concern were butyl-salicylate, which were used in our detergents. Butyl-salicylate has a health hazard for inhalation and absorption, and it's got moderate toxicity to aquatic organisms, and it was a voluntary elimination by there's no bans or anything in place that said you couldn't use butyl-salicylate. Petroleum hydrocarbons, those again are an inhalation health hazard. There's a potential for bioaccumulation. Again, that's a voluntary elimination. No existing bans that we were aware of when we used them. What we've been able to achieve, we've eliminated completely 3 NPE-based products from our product line. In fact, we no longer sell any NPE-based detergents at all. We were able to do that completely way before the voluntary phase-out went into effect between TRSA and EPA, which also gave our customers a benefit as well. Butyl-salicylate, within the detergents, we've eliminated 3 products that contain the butyl-salicylate. We actually have no butyl-salicylate in any of our products right now, and actually improved the safety of our products. When it comes to the petroleum-based solvents, we introduced a new solvent detergent product that was based upon a renewable resource, and that being a corn, soybean-based solvent that gave excellent results. Let me go on to basically builders. What builders do are basically improve cleaning performance of detergents. They remove impurities such as hardness ions. They maintain detergent's alkalinity, and they prevent precipitation and soap film when it's used. The standard builders that were used in our industry are basically EDTA and phosphates, and phosphates were very widely used in our industry. The 2 chemicals, both of the EDTA and phosphates, are chemicals of concern. EDTA is a persistent organic with hazardous degradation products, and there are existing state bans with EDTA in place. And phosphates basically cause eutrophication in lakes and streams, and there were existing state bans on the books where phosphates were not allowed in certain states, and therefore EDTA was used in that place. What we were able to do is formulate a new product that we call Structure. It's got an improved environmental footprint. It's a natural, sustainable, and biodegradable chelating agent, and it's based upon sugar beet waste, excuse me. It contains a very large proportion of renewable resources, and there's no bioaccumulation in the environment. So the criteria for structure was to resolve those downstream issues that the customers were encountering, to obtain DFE recognition on a builder, to have equal or better performance to our phosphate-based builder, and to have same cost and direct usage to our previous builder with no hidden costs or anything else associated with that. And we were able to meet those success criteria. So unlike the anticipated reduction goals in the Safer Chemistry Challenge, we thought this was a rather difficult challenge, and we only put a reduction goal of 50% down in this area. However, we were able to be so successful that actually we achieved 100% reduction in phosphates completely. So with that introduction of structure, we have been able to reduce 3.5 million pounds per year of phosphates going into the waste stream, and approximately 890,000 pounds a year of EDTA, which were big milestones and big improvements to our previous chemistry. We were also able to reduce surcharge rates for our customers in certain areas, so they didn't have to pay the surcharge for using phosphates in their facility. So what we've done is be able to, with structure, convert 100% of our customers in the U.S. and Canada to non-EDTA builders. We replaced it with renewable resource, that being sugar beet waste, and we improved worker safety and transportation safety of our product. With phosphates, we have obtained greater customer acceptance of our products, as one major chain committed to being totally non-phosphated, and another customer required it from the onset that we not use phosphate. It produced the same quality that the phosphate-based builder did, and that was required by our customers, and we replaced the phosphates with a renewable resource. And last year we were able to obtain DFE certification for that new builder. So where we are to date with what our achievements are, basically we've replaced all the nonylphenol alkoxylates, 100%. The butyl salicylate we totally eliminated in our products. EDTA and phosphates have been totally eliminated, and we're 100% free of those products. And we are working on being 100% elimination of petroleum hydrocarbon-based solvents. 100% of those have been eliminated from our detergents, but we still have some specialty products being used, and we're still working on that. But we have a good progress and good leads available to us to do that. So to basically show the benefits that we've given to our customers by going green with our detergents, our builders, and other areas, we've actually improved their environmental footprint. We have given them the same cost, ounce for ounce, and the same end-use cost. It doesn't cost them any more to use a green product than it did in their previous product. We have either same or improved wash quality. They're one-for-one direct replacements. They basically are just drop-in products. And we've actually continued to reduce the requirements for water and energy in their facilities. And they basically have been in compliance ahead of regulatory requirements. So some big benefits for our customers. Now, obviously, we've had some trouble identifying some alternative chemicals, and we've used these for chemicals to complete green screen. You see them listed here on your screen. I'm not going to go into all of them, but we do use other methods to identify alternative chemistry. So that's one of the difficulties with identifying alternative chemicals, is actually to get the data and see what it is. And the other is, as many of you know, usually biodegradable raw materials are more costly. There's obviously, we've had some difficulty. Nonylphenols were excellent surfactants, and it was difficult to outperform them or give equivalent performance. The solvent boosters are aiding performance, so replacing those hydrocarbon boosters has been very difficult. Another thing that we had to overcome when we went to NPE-free products is the physical characteristics of NPE-based surfactants lent themselves very well to liquid chemistry, and we had to overcome that with the NPE-free products. We also had some difficulty with compatibility with existing chemicals and applicability of some chemicals into our industry. So we still have some continued opportunities to being greener and to eliminate additional things. A couple things we're still looking at. We're still looking at new materials and the application process of those new materials. We continue to look at development for other laundry chemicals, such as the reduction or elimination of chlorine bleaches in our industry. And we also want to have further development of the laundry process so we can reduce water and gas, streamline product packaging, and we still want to concentrate even further our detergents and our products in general. So that's my presentation, and I wanted to thank you all for your time. And with that, I'll turn it back over to Jeff.
Okay. Thank you, Roy. Couple of questions. First one is, are washing systems products applicable for use in professional wet cleaning?
What do you mean by professional wet cleaning? I'd have to ask a follow-up question with that.
I'm reading the question as it's written. My guess is that it's the dry cleaning type thing.
Oh yeah, not in dry cleaning. In dry cleaners usually have several wet wash machines, and yes, they are applicable and can be used in that environment.
Okay, thank you. And the second question, how did you come up with sugar beet waste as the, and you don't have to get into any, trade secrets or proprietary information, but what led you in the direction of sugar beet waste?
Well, it had nothing to do, we were just looking for renewable raw materials, and that just happened to be where that one came from. We weren't looking for anything related to sugar beets. It's just that was the source that we found, and actually didn't know it was sugar beet waste till later on in the process. So it really had nothing to do with the process. We were just looking for a new renewable material.
Okay. Very cool. Good. Okay. Well, thank you. And again, if anybody has any other questions for Roy, we'll get to those at the end of the webinar. But we're going to move on now to Darlene Florence. Darlene is with Emery Oleochemicals.
Am I good to go then?
Yep.
Okay. Thanks, Jeff. So my name's Darlene Florence with Emery Oleochemicals, which is also here in Cincinnati, and most of you probably haven't heard of us either. We don't sell products directly to the consumer, but we go through distributors as we sell our chemistry. And I'll talk just a little bit about who Emery is and where some of our products go. So currently we operate on 6 platforms. I'm part of the AgroGreen platform. So I work with everything agriculture, which is everything out here, insect control, animal care, some weed control. I'll talk about those in a bit. But we also have the 5 other platforms, and so we have material that can go into engines, engine coolants, into different foams and insulations, with the home and personal wellness, things that go into shampoo and mouthwashes, washes and toys and tables and floors and all sorts of different things, into paints and things like that. So our materials are in a lot of materials that you won't necessarily know that. Our North American headquarters is here in Cincinnati. We also have a production facility here in Cincinnati. But our global headquarters is in Malaysia. It's in TPG over here in the South Asia. And they also have a production plant there, and then research facilities, sales and marketing facilities, and all of that. And then our third primary manufacturing is in the neighboring cities of Lochstedt and Düsseldorf over in Germany. But as you can see from the green, we also have sales and marketing kind of around the world, or at least in parts of the world. And so what Emery is the company's been around. We're actually celebrating our 170th anniversary this year. And so we started in Cincinnati, based in tallow and lard, so taking those fats to make our chemistry. But through a number of changes in the 2000s, we're now a joint venture between PTT Global Chemicals, which is a company in Thailand, and it's government owned, and they were told that they needed to get more into the green chemistry and the renewable chemistry. And then Sime Darby, which is a palm plantation in Malaysia. They're one of the largest, if not the largest, palm plantation, but they're also one of the key players in the sustainable palm initiative. So we've been green from the beginning and continue to grow on that path. Speaking about our AgroGreen Solutions platform in general, that business unit, we have mainly 4 product lines that we put into agricultural products. So we have our solvents and our adjuvants, our inerts, which are in our Emerine line. We have our Emerion line, which is the one that I'll talk about more, and those products are primarily for our weed and insect control or plant control. And then we also have our Emsol product, which is a plant growth regulator that's primarily used to control the flowering in tobacco plants. And then we have our Emerlife product that we've just started working with that is good for abiotic stress. We're still working on figuring out exactly how that works and where it works and things like that. That's one of our new products. So when we think of our Emerion products, we primarily have 2 products. We have our herbicide, which is based on the ammonium slope of fatty acids, and fatty acids are carboxylic acids. Primarily, when we talk about fatty acids, we're looking at the ones between 6 or 8 and in the low 20s. Those are the ones that are naturally produced. And so we have this fatty acid kind of the mid-range, and we've taken the ammonium soap of it, and it is a good non-contact or non-selective contact herbicide. So what it does is it will desiccate the leafy tissue by removing that waxy coating that's on the leaf. So every leaf has a waxy coating of various thickness to prevent the leaf from desiccating. And once the leaf desiccates, then it can't regulate its internal water pressure, and the leaf dies. And without leaves, you can't have photosynthesis, and the plant dies, depending on what type of plant it has. And then we also have our insect repellent, which is based on a blend of fatty acids, and it's repellent to a lot of different flying insects, particularly mosquitoes. And as one who mosquitoes seem to find particularly tasty, I can say that I've used it out in the field and not had any problem. I'm one that I have literally sat downwind of a bonfire smoke, sat in the smoke, and gotten eaten alive. So for this stuff to work is pretty excellent. And then at some of the lower doses, we're seeing that it might have some contact toxicity, and this is an area that we're looking at exploring. But for today, I wanted to talk about about our herbicide and one particular application that one of our customers actually brought to us. But before I get there, I wanted to talk a little bit about some of the green chemistry that we've been using at Emory here and how we go from this renewable feedstock, which is animal fats and plant oils. So that's what we've been using from the beginning. As I mentioned, here in the States, we primarily use beef tallow and pork lard, although just about all of it's from beef. And then in Malaysia, they use the palm kernel oil and the coconut oil. And then after that triglyceride bond is separated, so we get the glycerin separated from the free fatty acids. The free fatty acids are a mix. And then there's a relatively non-toxic methanol, as far as solvents goes. It's a fairly non-toxic solvent that is used to separate those fatty acids from each other, and then that solvent is then recycled back into the system. So there's the reduction of waste there. And then the way that we split our double bonds here on site is through an ozone oxidation. Before ozone oxidation became safe and economical to do on the large scale, there was a chromium catalyst that was primarily used, and chromium has a whole wide range of environmental problems, and so here we pretty much use oxygen and ozone. So it's an O3 and an O2. It's kind of fun. We get to say that we create lightning here on the plant site. And then once we've split that bond, we use both of those products. And the one product is actually our herbicide, and then the other product is a precursor to the abiotic stress material. And that fatty acids in and of themselves are fairly benign chemicals. They are readily biodegradable. Once they hit the soil microbes get really excited because they've found lunch, and so the chemicals don't stick around for more than 24 hours, and that then they're not noticeable in the environment, detectable in the environment from the background. So that's a little overview of our whole process. So when we look at our one product in particular with our herbicide, one of our customers looked at the OMRI listing for, this is for pesticidal soaps, and they looked at and they noticed that this restriction that a soap could be used primarily when it was used as a herbicide, it could be used as all sorts of farmstead maintenance, so roadways, ditches, right-of-ways, around your barn, around your perimeter, ornamental crops. And then they noticed that it could also be used as non-food crops. And they were in conversation with some folks down in Texas that were looking for additional chemicals or any chemicals to use as a defoliant prior to harvest in cotton. And so vinegar's a chemical that will defoliate the crop, but at 20%, which is about what's useful, it's not particularly safe to use. So they were looking for something that was a lot safer. And so I'm going to go through a little bit about cotton, since I'm not sure kind of who's familiar with cotton. I know I certainly wasn't when I first started working on this. And then talk a little bit about what we found based on what this customer, the testing that they did, and then the testing that we've done. So as many of you do know, that cotton is a warm season crop. Certainly we don't grow it up here in Ohio. It doesn't like cold, it doesn't like snow, and so it's grown primarily south of the Ohio River, which runs along here between Ohio and Indiana, and then kind of south of this sort of arbitrary line. And it's grown in 5 main regions, which I have circled. And there were about 9.3 million acres that were harvested in 2012. And so the previous slide had mentioned that only about 10,000 or so of those acres were organic. And one of the reasons is that cotton is a fairly heavy pesticide crop. A lot of things fine. The cotton plant, the cotton seed, the cotton boll, the white fluffy part, very tasty. Insects and diseases both, and then weeds will compete anytime you have a warmer climate like that. You don't have a good frost kill like we were fortunate enough to have in the north. And there are primarily 2 types of cotton that are grown in the United States. The upland cotton, which you can see is the primary cotton that's grown, and then the Pima cotton, which the Pima cotton has a little bit longer fibers, and so the woven products end up to be a little bit softer and a little bit higher quality. Pima cotton is similar to Egyptian cotton, so you can kind of think of it that way, whereas upland cotton is more of the everyday cotton, blue jeans, t-shirts, all of those sorts of things. So why would we use a harvest aid in cotton? Why not just let the plant naturally desiccate as the season gets a little bit colder, as the plant kind of runs out of nutrients and those sorts of things? And one of the reasons that's not on the slide is that cotton is actually a perennial crop that's grown as an annual crop, and so there needs to be some way to tell the plant, produce seed, produce the cotton, and be done. And so we can see that there are these 2 paths that we can take from the cotton plant being open, that when we defoliate, we can see that these leaves are falling off the plant, they're dying, and then they're falling off, ideally, and that ideally a product would help open these bolls of cotton that aren't open, so you can have a plant that's just cotton with all the leaf trash at the bottom, and you can harvest that. So you can see this picture that these leaves are dying. We didn't get too many cotton bolls in this picture, but you have the cotton that's a little bit easier to expose. You don't get as much trash in your combine when you're harvesting. The cotton then stays whiter, which is also more desirable. Whereas here is if you don't defoliate, then you don't get the cotton bolls that open. You might have some that die before you can get into harvesting. You have only a few leaves that fall off, and you run into some troubles that way. That you have some more trouble running your cotton through the combine. You might not get as much high quality of your cotton, and that you might have, the longer your crop's in the field, especially if you get some rain in the fall, you might have some rotting. So we looked at a couple of different years, and the first year we just ran our ammonium nonanoic product, which is our herbicide product, and we ran it at 5, 9, and 18% active ingredient. It's only 40% active ingredient to start with, and so that can sometimes create a little bit of entertainment within that. And then we ran it against paraquat, which is one of the industry standards. Paraquat in of itself is not a particularly safe chemical. It can cause some human toxicity, unlike a lot of the other herbicides, but it is incredibly effective. And so what we have here is we have our 4 treatments plus our untreated control, and then the way that this slide and all the rest of them are laid out is that this is the value, so this is the percent desiccation for each of the products, and then the letters afterwards. If the letters are the same, then we didn't have any difference with the treatments, and then if the letters are different, then we saw difference in the treatments. So for desiccation with 10 days, which is right before they took harvest, that we can see that all of our products provided better desiccation than the control, and that our ammonium nonanoate product provided this equivalent desiccation to the paraquat, which is the industry standard. We can also see when we look at the number of green leaves, so leaves that are fully green and looking really well, the that the two higher rates of ammonium nonanoate performed as well as the paraquat. We didn't see any difference with the open poles, which indicates that the ammonium nonanoate is only a contact product, which is what we thought, and doesn't have any full opening effect, which is disappointing, but it's not outside of what we expected. And then the defoliation matched well with the green leaves that we saw, that we had the higher two rates were equivalent to paraquat. So this was promising and really exciting that we could then look at what we could do a little bit more of a in-depth trial. So in 2013, we also looked at these and a couple others. But one other thing we looked at is not just what the product looked in the field, but was there any effect on the fiber quality? And so we wanted to make sure that that the ammonium nonanoate didn't have any adverse effect on the quality of the fiber, since the material does go into fabrics. And so if we look at these first 4 quality measurements, we didn't see any difference between the control, the material, and the paraquat. So the ammonium nonanoate wasn't having any beneficial or detrimental influence on those products. But then when we looked at the elongation, which is the length of the fiber, and a higher value is a little more desirable there, we did see that the ammonium nonanoate products were increasing that elongation, which is indeed a desirable effect. And so we wanted to see if this was occurring in multiple years. And so we looked again at 2013. We looked at this. We looked at the treatments, and so we have our same 4 treatments plus our control from 2013, but then we also added 2 other treatments. So we added a systemic product, and then we had a systemic product mixed with a product that opens the bolls. And you could see that early in the season that there wasn't much difference between desiccation, the open bolls, and defoliation. And even later in the season, again, they harvest about 11 to 15 days after the treatments are put on, that we didn't have any difference in desiccation, and that there wasn't, especially with the highest rate, that there wasn't a difference with the material that had the boll opener or with the paraquat. So this is a little bit different from the 2012. Again, different. One of the things when working in the field, you have different weather conditions, and so that likely explains some of the difference there. And then I didn't show the fiber quality difference here, but we didn't see that elongation another time. And then we also ran the data of, this is to show you just to show some pictures of what your desiccation would look like in your control. So only about 30% desiccation there, as opposed to 93, 96, and 90. So just taking these 4 treatments out to get kind of a visual idea of what that would look like. So in 2014, we had the same treatments as 2013. The weather, however, was a little bit different for 2014. In most of the country, there was a late season cold snap, and so early November, we just had this week of just unusual cold, and then after that, it got warmer again. And so when we look at our desiccation numbers, paraquat still did okay, but we have much lower numbers for our ammonium nonanoates and for our other products. And we especially have fairly low numbers for our defoliation. If we look back, we're looking in the 80%, 75, 80% in 2013, and in 2014, our highest one was at 74%. So we had quite low desiccation, defoliation, but still had better defoliation than the control, with the exception of the lower rates. And so this was all done at university trials. Commercial growers likely would have gone in after, when that warm-up occurred after that cold snap, and sprayed a second time. And most of them will use a a nozzle that sprays the lower and upper canopy at the same time. So that would also help because this year they saw some excessive vegetation. And the fiber data for this year hasn't come in yet, but we don't expect to see any differences. So our marketing folks and sales folks started talking with some of the growers in Texas to see, okay, can we, put this product out on a much larger trial, a much larger field, put it out on a commercial field and see how this goes. And then we reviewed our OMRI label that had been renewed at in 2014 and discovered that the non-food crop use has been taken out of the label. And so we're in the process right now of discussing with OMRI, discussing with the National Organic Standards Board and National Organic Program to figure out what was changed or why this was changed and why we weren't really let know of it, that this was a change that occurred in the label and in the restrictions without our knowledge until we started looking at this for cotton and had some success for cotton. And so with that, I'll take questions if there are any, if there's some time, and then my contact information is here, and then the other members of my team here in the U.S. Thank you.
Okay, thank you. So we have a couple of questions, and actually they would apply to both of our speakers. The first question, was there any resistance within your company regarding the change to greener products?
You want to answer? For us, we've always had fairly green products and green processes. So that's part of the business model and has been so for 170 some odd years.
This is Roy. Yes, from our perspective, once we gained initial acceptance by the leadership team, no resistance at all. It was a little bit to overcome initially because they thought it would be very difficult for us to develop green products with the criteria that we had set forth. So once that was accepted, though, it's been good ever since then.
Okay. And also for both, how does your progress compare with other of your competitors in your respective fields or industries?
This is Roy. We've been ahead of our competitors just because we've gotten just ahead of the curve because we started basically earlier than they did, and they're still playing catch-up. They do have green products, but they're still basically just a generation behind us because we started earlier. So that's our position.
And this is Darlene, with our green products, we've had about the same kind of time from discovering like our ammonium aminoate, discovering the product and starting working with the license and running the required efficacy data. So from that time to registration can vary with products, but from registration to market sales for most products is about 5 to 7 years, and that's what we've been seeing. So I think the industry, agriculture, is looking for greener products, for products that are safer for the consumer and are especially safer for the farm worker and the environment.
Okay, great. That's all the questions we have for now. I do want to ask Dave Folks, would you like to, I'm unmuting you, if there's anything you'd like to add about the Ohio EPA P2 program, since you were involved in helping obtain these presenters for us.
Sure. Thanks, Jeff. And I'd like to thank both speakers for taking time to provide information and background about their green chemistry programs and all that, especially since, they had already been committed to the AWMA P2 conference we're going to have in January. So I'm glad we were able to have a couple speakers actually get their presentations out there. Real quickly, I'm Dave Folks with the Ohio EPA Office of Compliance Systems and Pollution Prevention. I know it's a mouthful, but my main focus is providing technical assistance related to pollution prevention, waste minimization, and sustainability to businesses and others in Ohio. And in fact, I've worked with Washington Systems in the past on some of their activities, which I'll go into real quickly after I do my little intro. Our office is unique within Ohio EPA because it's a non-regulatory office that provides free and confidential assistance to Ohio businesses on the compliance assistance side and pollution prevention. One of the main ways we deliver our pollution prevention message is through on-site assistance, where we review a company's process operations and help identify where they can change existing processes, adopt new technology, substitute materials, improve their operations through pollution prevention. So where does this fit in with green chemistry? Well, like you saw in some of the last two presentations, many of the basic concepts of green chemistry are familiar to P2 pollution prevention practitioners. The concepts of substituting less hazardous materials into chemical formulations, reducing waste, have been around for many years. But green chemistry has taken these concepts and expanded the scope of possibilities by fully evaluating all aspects of chemical reactions, processes, and formulations. So generally speaking, green chemistry is designing efficient, effective, and environmentally benign chemicals and chemical processes that can largely capture, that basically capture the concepts of green chemistry. So I wanted to mention briefly that Washington Systems was recognized by Ohio EPA under our Encouraging Environmental Excellence program last year in 2014 for many things that Roy talked about, their ongoing commitment to protecting the environment, conserving natural resources, and including their green chemistry efforts. So that's pretty much all I have to say because I know I'm at the end of our webinar and I don't want to take everybody's time. So thanks, Jeff.
Okay, thank you, David. So again, just a reminder to everybody, the recording of this webinar will be up on the NPPR website. And thank everybody for their attendance, and especially want to thank our two speakers for a fantastic job in presenting their case studies. One final question. Did you, and this is for Darlene, and that's, did you look at the impact of water use after the application of the ammonium?
No.
Yeah.
So, well,
Yeah.
I'm trying to think. The cotton wouldn't be watered after the material is applied. We looked a little bit at if it shortened time to harvest, and at least in the university trials, it didn't look like it shortened time to harvest a whole lot, but we might see that it does when we get into bigger scale trials on actual production fields rather than university fields. So I hope that answered your question.
Okay, great. Okay, thanks everybody, and we'll be like I said, we'll be posting the recording, and keep on the lookout for the next Safer Chemistry Challenge program webinar.
Thank you.
Thank you.